Hi, Phil Malone here. This is part 3 of my FTC state machine example. Part 1 was a discussion on the principles of a state machine. Part 2 was showing you how to create a state transition diagram. And Part 3 is a walkthrough of the code that executes the state machine opMode. If you'd like to go to one of the first two sections, just click on this title graphic and it'll take you right to the videos. But other than that, let's get right into it. Alright, so here's the code that I'm using to implement the state machine I've discussed. This is in the A2818 statemachine.java file, and this can be added to any project just by transferring it into the same folder as all the other opmodes. So the first thing I do at the top here is I describe what the state machine is doing. I go through and I list the actions that are happening in each of the states, or I describe the states to be more accurate here. And that's in this first section here. If we scroll down to the code section, this is where we declare the opmode. It's the A2818 state machine opmode. And the first thing I do is I create an enum, or an enumerator, called state. I define it and then I enter in names for all the states. You notice I'm consistent in how I do this. I start with state underscore and then put the name of the state, which is as descriptive as I can make it in just a few words. You can add and remove states from this at any time. The system keeps track of them all, and so it's very easy to add states. So these are our states: initial, drive to beacon, locate the line, follow the line, square to the wall, deploy the climbers, drive to the mountain, climb the mountain, and then stop. Alright, so I'm going to scroll down here. The first thing I do is I have two different paths that I'm going to follow in this autonomous routine, one to get to the beacon and one to get to the mountain. And I've declared these two arrays of path segments. Now, pathseg is an object which I declare at the end of this file. It has three members in it. It has a left and a right distance, and then it has a speed. So these three numbers. So this first path segment has three segments in it. The first one, the left wheel goes forward 0 inches, the right wheel goes forward 3 inches. And then it does this at 0.2 speed, or 20% speed. And this is just to pull the robot away from the sidewall and point towards the beacon on the other side. Then the next segment is 60 inches left and right wheels at 0.9. This is purely a guess at how far across the field it is. As I say, this is not a tested routine, this is just an example. And then the third segment turns, it says left here, but this is going to turn to the right. This is a bug, I'm going to have to change this. But anyway, so these are three motions defined in inches and speeds. Then there's another motion that we have declared here, the mountain path motion, and it has four segments. It backs away a little bit, it backs up a lot, it turns to the right backwards, and then it goes forward to approach the ramp of the mountain. So we're going to use these two names later on in the code. Then I go through and define some constants, or some finals as they're called in Java. One of those is how many encoder counts per inch do I expect. This is also a made-up number here. This would be calculated based on the wheel diameter, the gear ratio, and the encoders that you're using. Then we have a couple of constants that we're using for comparing thresholds. We have a value that we use to determine when we're seeing the white line on the ground through the light sensor. We have a value that says when we're going to hit the wall with the optical distance sensor, and then we have two position values that are used with the servo. A position of 0.1, that'll be the retracted position, and a position of 1.0, that will be the climber deployed position. So these all just get defined up in the header up here just to make it nice and neat. I hate having just numbers in the program. I like to use words so that we can see what's going on. Then next we go in and we declare and initialize the objects that are going to be used to talk to the hardware. So in this case we have two motors. We have a DC motor called left motor, one called right motor, a servo called servo, and a light sensor called light, and an optical distance sensor called distance. You notice that all of my variables are prefixed with a lowercase m, just to indicate that they're a member of the class. Then I have two integers that I declare, which I use as holding places for my encoder targets. There's routines that enable me to drive certain distances, and what they do is they set an encoder target locally, then they tell the actual motor controllers to go to those positions, and then I can compare the current position with the requested position to get to know when I've reached my target. Next, we declare some time variables. We have runtime, which is the overall time in the match, and we have another time called state time, which we use to record how long we've been in a particular state. So whenever we change state, this gets zeroed out. And we've got a couple of variables we use for keeping track of what the system's doing. So we have a state variable, it's called current state, and it's of type state, which means that we can put any of those enumerators in here. It's nice that the system will keep track of this for us. We also have a pointer to an array or an array object, which is going to hold whatever path we're currently following. And we also have an integer which is telling us what segment of the path we're currently on. So these last two are used for our autonomous driving. So that's really the setup for all the variables. Here's the constructor for the state machine, the opMode. Nothing done there. Here's our init function. So this is the first function that's called when the driver station gets its init button pushed. So this will happen. You'll select an opMode and you'll hit init, and that's your way of telling the robot it's time to configure any of your sensors and things to certain positions to get ready for the match. So in this case, what we're doing is we are getting handles to access the various hardware components. So we're saying get the DC motor called motor left, get the DC motor called motor right, and we tell it that one of those is reversed. We do the same for the light sensor and the rangefinder, and finally we do it for the servo. So these are basically getting our handles for accessing these. We do this in the init function so that if there's any problems with these names, we find out before the match starts. Then the last thing we do here is we set the position of the servo to climb or retract. So this is our way of putting the servo into its startup position so that it fits into the sizing box. So you do that in the init, and then it'll hold that position until the match begins. Last thing we do here is we set the power to the motors to 0, 0. They should already be stopped, but this just guarantees it. And then we set the mode of the encoders to reset. So we're going to tell the motor controllers to reset the encoders. So this is all done once in the when we hit the init button. Then until we actually start the match, the init loop method is called, and what this is doing is continually sending the reset encoder command just in case the person is moving the robot around. And while it's doing that, we're sending telemetry data, which is displaying the current left and right positions of the motor encoders. So we can watch to see what's happening on the field, and we can make sure visually that the encoders are reset before the match starts. So of course none of this has anything to do with the state machine yet. This is just basic setup. When the driver hits the start button, the robot will do these actions in here. It will set the drive speed to 0 again. It'll now change to run to position, and that's because we know the first thing that the code is going to do is start following the encoders, moving the encoders. We reset the runtime, so that says we're starting the clock back to 0 at the beginning of the match. And here's the first thing we do with the state machine. We call the new state function or method, which is declared locally in here, and we pass it the state that we want to go to. So we're setting it to state initial. So this is the first state in the state machine sequence, and we use this just to make sure everything's set up. This call is what we'll use to always change the state. We could just put a value into the variable, but we use the new state function because it not only sets the state, but it also resets the state clock for us. Then we drop into the main driving loop. So this loop is running continuously all the way through game time, and this is where we're really running our state machine. So every time through this loop, we're going to do one thing every time, and that is we're going to display the current state and state time as part of the telemetry data. So line number 0 is going to be the current state. So we can watch on the driver station and watch the states progress through the operation of Autonomous. So this is kind of a really neat diagnostic thing. And then we drop into the state machine itself. So the state machine is effectively a large switch statement based on the current state. So what this is doing is this is saying what is the current state, do the case associated with the current state. So in this switch statement there's a block of code, one for each case, and that block of code implements the current state. Every time we enter a case, it's going to do three things, one of three things. First, it's going to look to see if there are any events that will cause a state change. So this is the first thing we do. So it's usually the condition for the first if in every state. If there is an event, we've found an event that we need to action, we take the action and then we set the next state. If there is no event, we do whatever processing that the current state needs, and usually then we send telemetry data for this state. So this lets us send the appropriate data to the user interface on the driver station based on what state we're running. So let's look at an example. So the first state in here is state initial. So this is where it's going to come the first time into the state machine. And we're looking for the event that'll get us out of this state. And in this case, that event is encoders at 0. So this is the function we have in here, and it's just checking to see whether the encoders have been reset correctly. So if this returns a true, that means that we have our event that we need, and then we're going to action the event. And that to action the event, what we're going to do is we're going to call the start path function and pass it the array of segments that we need to get to the beacon. So we're saying, okay, we're good, whereas encoders are at 0, start the path to get and run the beacon path, and then set the new state to be drive to beacon. So if encoders are good, take an action, set the new state. Otherwise, do whatever we need to do while we're in this state. And currently all we need to do is just display the telemetry data. So what we're going to do is display the left and the right encoder positions, because if we're sitting here looping in the state, it means the encoders aren't at 0, so it would be nice to see what they are. So there's the first state. Once it's done either of these two steps, it exits out and will go all the way to the end. Loop will exit and give control back to the FTC underlying code, which will control the devices, read the sensors, and then come right back in again at the top. So let's look at the next state. So the next state, which we get to by the encoders being at 0, is the drive to beacon code here. So once again, we always look for the exiting event first. So we say if PathComplete. Now PathComplete is a function that's also declared further down. It's a sequence of operations, and PathComplete will attempt to drive the complete path as defined by the path that we set up on the way in. When it gets to the end of that path, when it's done all the legs, PathComplete will return a true. So if PathComplete returns a true, it means we've got to the end of the current path, in which case it's time to move on to the next event, to the next state. So if the path is complete, this is what it's going to do. It's going to turn on the light for the light sensor, because it's now going to start looking for the white line. It's going to set the drive speed with a small negative and a small positive, so it'll start the robot rotating to the left, and then it will set the new state to be locate line, because what it's going to do, we want it to start rotating to the left until it hits the line so it can track it. If we haven't reached the end of the path, then what we're going to do is we're going to display some diagnostic data, which is going to tell us what segment of the path we're on. So it's going to say 2 of 3, meaning the second of all 3 segments. Then it will show the target encoder value and the actual encoder value for the left wheel, and the target and actual for the right wheel. So we can watch these numbers on the driver station as the robot drives along. PathComplete is, like I said, it's a series of routines we'll look at a little bit further down. Anyway, when the path is complete, you see the next state is state locate line. So next time we come in, we're going to drop down to state locate line. Now the thing to remember here at all times is that every time we come into this loop, we execute one pass through this code, and then we drop back out again. So we're not hanging in here, we're just looking to see what's going on and then returning. So now we're in the locate line path, and we rotating left until we see the line. So what's the event condition that's going to get us out of this? It's going to be that the light detected level is greater than the white threshold, which means we're going to keep on in this locate line code until that threshold is hit. When that threshold is hit, we set the speeds to 0, and then we set the new state to follow line. So we're going to say we've found the line, now we're going to follow it. If we don't see the white threshold, once again we don't really have anything to do because we're already rotating, so what we're going to do is we're just going to display diagnostics data. We're going to display what the light is currently being read and what our threshold is we're looking for, so we can watch the driver station and see it trying to find the white line. So when that line gets hit, we're going to go to state follow line. So that's going to drop us down to here. So when we're in follow the line case, what we're doing is we're tracking the white line. We're trying to track on the right-hand edge of the white line towards the wall. So the exit condition, the event that will get us out of this state, is when we get close enough to the wall. Distance sensor gives a reading greater than the range threshold. So if that happens, it's time to stop following the line. So what we'll do is we'll switch to constant power, and then we'll set the drive speeds to 0.2 and 0.2. What this is going to do is start us pushing against the wall because we want to square up. And we'll set our new state to square to wall. So that's setting us up for our next action. If the distance sensor is less than the range threshold, that means we haven't got there yet. So what we're going to do is we're going to steer left or right based on which side of the line we're on. So if we're actually on the line, we're going to scan to the right, we're going to steer to the right by driving the left wheel, and we're going to display some diagnostics data, which includes a little arrow that's going to point to the right to say that's the way we're going. If we're not on the line, which means we're on the right of the line, then we're going to scan to the left by running the right wheel and put a diagnostic string up with a little left arrow. So once again, we're doing the same thing. Check for exit condition, do the exit if we want to, if we need to, otherwise do our basic processing. So when we exit out of this state, we're going to go to square to the wall state. So let's have a look at square to the wall. Remember, this code is just trying to push up against the wall, and what it's going to do is it's going to keep driving forward for a second, and once it's driven for a second, it's going to stop and deploy the climber. So that's what happens here. Every time we come in here, it's going to check to see if the state time is greater than 1 being 1 second. So if the time is greater than 1 second, it's going to stop the motors, set the servo to the climber deploy position, which is going to like throw the guy out, and then set the new state to deploy climbers. If time is not greater than 1 second, it basically won't do anything. It'll just sit there, exit out, and come back again and again. It'll keep on looping and coming back to this state until the time is greater than a second. So moving on to the next state, what this is doing is it knows that the last thing we did was to move the servo, so it's going to wait 2 seconds for the servo to move all the way out, for the climbers to fall out, and for everything to settle. So it's going to do similar to the last piece of code. It's going to check the state time, wait for it to be bigger than 2 seconds, and when it is, it's going to put the servo back into the retract position, so it's going to pull the servo back. It's going to start a new path because it's heading off to the mountain, so it's going to call the start path code, tell it I want the path to the mountain, and then it's going to set the next state to drive to mountain. So once again, same thing. We check our exit condition. If we have an exit condition, we take an action, change the state. If not, in this case, we don't have anything to do either because we're just waiting 2 seconds. Let's look at the drive to mountain state. This should start looking pretty familiar now. So we're always going to check our exit condition. Now, exit condition is the path complete? If it is complete, it means we've got there. So now what we're going to do is we're just going to drive up the mountain with constant power. That's kind of, what we're assuming this robot's going to do. So it's going to set constant power. It's going to set the power to 50% on both wheels, and then it's going to set the state to climb mountain. If it hasn't completed the path, it's just going to display the diagnostics of what it's doing, same as before. It's going to display what segment it's on, what the encoder values are, and what the encoder values, the targets are. So this will just update the screen as it's driving to the mountain. Once it gets to the climb to mountain state, what it's going to do is it's going to climb at whatever power we set for 5 seconds. Drive up the mountain. So we're going to do that same thing. We're going to wait. We're going to see if the time is greater than 5. Here's our exit condition. We're going to drop back to constant power. We're going to set power to 0. And our next state is the stop state, which is our final state. Otherwise, while we're driving, we're just going to display the encoder positions, just for the heck of it, just so that the pilots have got something to. The drivers have got something to do during autonomous. This could be handy if we ever wanted to switch to driving a certain distance, but for right now it's just for show. And then finally the last state is the stop state, which basically doesn't do anything. So it'll just sit there in the last condition it was put in, which was 0 power to the motors. So that's the full sequence. And there's a fair bit of code there, but each state is fairly simplistic, especially if you follow the same strategy of checking for the exit conditions, and if there's no exit condition, doing your default state. It's also handy to put some diagnostics in the form of telemetry into each one of those states and customize it based on what's going on in that state. Show the driver or the test, whoever's testing the autonomous, as much information as possible based on the state that you've got. Alright, so the last built-in function is the stop function, in which case that gets called at the end of the match, and we just switch back to constant power and we set the drive power to 0. So that's the main, they're the functions that are going to get called during the match. I want to show some of the functions that we built to support that. So here's the new state function, and it's just passed the state, and you'll see it does two things. It resets the state time and then just loads up the current state member with the value that it was passed to it. So nothing elaborate there, but it does two things, so we put it in a function. Now we have a series of functions that let us manipulate the destination for encoder values. So this is the set encoder target, and what we do, we pass in the left and right encoder value. We do two things. We load them into our local members, and then we pass it into the set target position for the motors. So we say, take the left encoder value that was passed, put it into our member, so we take a copy of it, and then pass that into the left motor set target, and then do the same for the right. In this case, we're actually taking the absolute values and loading them into the encoders. The other version of this is the add encoder target, which does a similar thing, but instead of just copying the values, it takes the numbers that are passed in, adds them into the current encoder target member, and then passes that in. So when we call add encoder target, we're really saying it's a relative move. We want to take these values that I've given you, add them to the current target, and then issue that again, so it'll move relative to the last move. This is different than saying move 100 counts from where you are now. It's saying actually move 100 counts from where you moved to last time. I prefer to do it this way just because it tends to minimize errors that accumulate from over, moving too far or moving not far enough. But there it is. So then we have a sequence of routines that let us set the motor style in a single call. So we have set drive power and set drive speed. You'll notice that set drive power takes the values that we pass in, the left and right power, clips them, and then sends them to the motor controllers. And then the set drive speed essentially does exactly the same thing. It takes those same values and passes them to the set drive power. The reason we have this second one, the set drive power, is purely for the sake of making the point that when you call this function, you realize that you're setting the speed of the motor using the encoders rather than the power of the motor that just sets the voltage. They do the same thing, but it's just a reminder. Then we have some functions that set the mode of the motor controllers. So run to position sets the motor controller to the run to position mode. Use constant speed sets the motor controller to run using encoders, and use constant power sets the motor controllers to run without encoders. So these are just functions that just make it easier to set the more elaborate motor conditions. Couple more. One for resetting the encoders, and we have a function to reset the drive encoders because we want to do two things. We want to actually set our own target values to 0, as well as telling the motor encoders to reset the encoders. That's so that the hardware gets reset and the software values get reset. We have another one that is sync encoders that takes the current positions from the actual encoders and puts them into our local variables. That's our way of just getting a copy in software of what the hardware is actually doing. We use this when we start a new path, so that we start the path with the hardware and the software agreeing on where the robot is. And then here's our final helper function here that in one command takes the desired motor mode and controls the left and right hand motor to put them both in the same mode. So a lot of this code could be done in line, but I like to take the detailed calls and put them in one place and just have a single call that makes it easier. A couple other calls, one for getting the current position and one for left and right. These were put in as separate functions because initially we had to negate one of them because the code wasn't working quite right in the built-in code, but now that's corrected, so these probably are redundant. We don't really need those, but they're there for posterity. Another call we have here is MoveComplete. Now this is different than PathComplete. MoveComplete is used to determine whether the motors have reached the encoder values that were commanded. So this is our way of knowing when we tell the drive motors to go to a certain position, left and right wheels, we can verify that they've reached that position. And we currently do this by comparing the actual position with the requested position and making sure that it's within 10 counts of where we asked for. There is a busy flag that's returned from the motor encoders, but this is still under development and doesn't give us exactly what we want. So right now we're just doing it by checking the values, but hopefully eventually we'll be able to use the isBusy function. Another piece of code is encoders at 0. This is checking to see if the left and right encoders are close to 0, in which case it returns a true. We use this to verify that the reset has been actioned correctly. Now we have some code here for the driving sequence. Now this is used so that we can have those list of segments that we want the robot to drive, and these functions will step through them one segment at a time and eventually return a true when they're all done. So we have a couple of different operations. We have a start path, we have a start segment, and then we have a PathComplete call. These three work together to do the motion. So whenever you want to start a new sequence of movements, the code calls start path and passes it an array of segments. So you saw we declared two arrays of segments at the beginning of the program, one for the beacon, one for the mountain. So we could pass either of those in there. When that gets passed in, what we do is we save the path. So say, okay, the current path is now this new path, so whatever it was. We set the current segment to 0, which means we're starting at the first segment in the array. We sync the encoders, which means we read the current encoder values and load them into our local target members. We set the motors to run to position because we want them to start following the encoder targets. Enable. There we go. And then we say start segment. And what start segment does is actually loads the first set of encoder and speed values into the motor controllers. So we'll see that. So start path is called once at the beginning of the path, and then we start a loop. So start segment, its job is to start a new segment. And what it does is first it checks to make sure there is a current path. So it says if the current path is not equal to null, it knows it's got something to do. And then my typing is really bad over here. And then what it does is it gets from the array the value of distance for the left and right wheels, multiplies them by the counts per inch to come up with how many encoder counts the wheels have to move by for left and right. It uses the add encoder target function that we saw earlier and passes in those values, so that will figure out where the new encoder values need to be, and it will set them. And then it reads the speed value out of the array and loads that into and does a set drive speed. So it sets everything up ready to go, loads the new target values for the encoders and sets the speed, and that will start the path running because the motor controllers will take over at that point. And then what it does is it increments current segment so that next time it comes in here it'll be ready to do the next segment of the path. So that's starting one segment. Then all we have left is the PathComplete function, whose job it is to determine whether we're finished. And so first thing it does is it says, is the current move complete? Meaning, have we got to the end of the move? If we haven't, it doesn't do anything. It just returns false. If it has got to the end of the current segment, it looks to see whether there's another segment to do. So is the current segment less than the length of the array? If it is, it means there's another segment. So it calls start segment to start that segment. If it's not, so if there's not another segment to do, it says, oh, well, I must have just finished the last segment, so I'll set my path to null, I'll set my segment back to 0, I'll stop the motors, I'll switch back to constant speed, and I'll return true to say, hey, my path is complete. And that's what's required to do the driving a path. All in all, it's actually pretty straightforward just with the 3 small calls, and all that's left at the end here is the class definition for that path segment that I talked about. This is what we use to build the array. So just as a refresher, this is our driving the path, and if I go all the way back up to the top here, You can see where we declared the paths right here. So here's our beacon path and our mountain path. So you can add as many different paths as you want just by declaring more more arrays of different paths, building them with inch distances for the left and right wheel and speed, and you can have it to do whatever you want, and then just you can run that path just by doing a start path and then a path complete call. A lot of things to do there, a lot of different elements, but hopefully the code is consistent. You can see how you would adapt it to different sensors, different sequences, and the code can be downloaded. There should be a link on the video, and you're looking for the A2818 State Machine Java module. Thanks very much. I know it's been a long description, but I appreciate you listening in.